So we are, can I make that go away? There we go. We're going. Okay. So this is our first day of trig. So I'm introducing the unit circle to you guys. I'm only going to show you the unit circle with angle measurements in degrees. Next class, we're going to talk about radians. And we're starting with degrees because you guys are familiar with degrees from geometry. Yes?
No. Yeah.
Angle measurement in degrees. Okay. And then we're going to look at how you guys can evaluate trig functions using the unit circle. In geometry, you guys studied a little bit of right triangle trig, SOHCAHTOA, right? SOHCAHTOA rings a bell. You remember SOHCAHTOA. You may not remember what it is.
Sine is over hypotenuse. I was confused morning, but I don't remember what O and A is.
Okay, well, we'll talk about that.
Opposite over hypotenuse, and then it's adjacent over hypotenuse, and then opposite over adjacent.
Okay.
Nice job.
Shh. But I'm going to show you guys how you can use the unit circle as a reference to be able to evaluate the different trig functions that you guys are familiar with. Okay, so similar triangles, right? That's something you guys also should be familiar with from geometry. And similar triangles look identical in shape, but they might not be the same size. So they have to be similar in shape, they have to have equal corresponding angles, which if these two triangles are similar, then that means that this angle must be equivalent with this angle, and this angle must be equivalent with this angle, and this angle must be equivalent with this angle. Also, for similar triangles, so if I said this side was A, B, C, D, E, F, the ratio of side A to C would be equivalent to what ratio?
B over E, or B over F. Or I like a little different, that's why.
Which one?
D over F.
D over F. Okay, or like C over B, that ratio would be equivalent to F over E. Okay, so that's the idea behind similar triangles. We're really going to focus on a specific type of similar triangle now, which are similar right triangles. But first, let's just introduce right triangles. So right triangles are triangles that have one angle equal to 90 degrees, meaning that the other two angles must be complementary. Complementary angles are two angles that sum to 90 degrees. So if one angle is 90 degrees and the other two must sum to 90 degrees, we know that the angle sum of a triangle is 180 degrees. Okay, so we're just kind of doing a brief overview or review from geometry. Now, we have a picture of a right triangle here where the two sides that form the right angle we refer to as the legs of the triangle, and then the side that's opposite the 90-degree angle we refer to as the hypotenuse. Okay, so the side opposite the right angle. Now, there's two different special right triangles that you guys should be familiar with. So the 30-60-90 triangle and the 45-45-90 triangle. And I'm going to show you guys how to derive the side lengths of those types of similar right triangles. Okay, are we good so far? So I'm going to do my best attempt at drawing an equilateral triangle. What do we know about an equilateral triangle, Case? You're raising your hand. Oh, okay. What's your guess? If we have an equilateral triangle, what do we know is true about it? Equal sides. Equilateral triangles have equal sides, meaning that they also have what? Equal angles, where each angle would have to be a measurement of what?
60.
That's not Yes, 60. Sorry, I was commenting on my drawing of my equilateral triangle. Okay, that kind of looks like, we're gonna say that's an equilateral triangle, right? It's good enough. Okay, so we know that each angle, if it's an equilateral triangle, has to be 60 degrees. And we know, I'm going to say that each side length, and you'll see why in a sec I'm saying, each side length I'm going to refer to as 2x. So I'm deriving the side lengths of the 30, 60, 90 triangle. So now I'm going to drop a perpendicular bisector to create two right triangles. And I'm just going to redraw one of those right triangles.
Triangles, why?
Oh, and that's why it's 30 and 60.
I don't like
That's smart.
geometry.
It's
Oh,
not
trust me, I hate
geometry.
geometry. This makes sense though.
This is not geometry. Geometry is proofs and theorems.
This actually is geometry.
It's not as bad as proofs.
Okay.
Can you promise us that we're never gonna do a proof again?
That's so not true. After like calculus, that's all you do.
Well,
Can I not
what's
take
after
fast
calculus?
Like
Isn't
linear
it multivariable
algebra.
calculus?
Linear algebra.
All
right.
So easy.
You guys.
Sounds like the easiest.
Shh.
Yes.
Linear algebra.
Hey. So draw your right triangle. So now, what is the angle that's in the corner closest to me? 60. And then what will that remaining angle be?
30.
30.
You have a sticker that says I love math.
This side will be 2x. What will the bottom part of the triangle be? This
X.
x. Do you guys see why I made each side 2x now?
Yeah.
Smart.
But we don't know
Just be one half that.
what this leg of the triangle will be.
Isn't it like root 2x or something like that? Something annoying.
We're driving it.
A square.
Oh yeah, that.
'Kay. It's a bit. So we need to derive what that side length is going to be. And we're going to use, Ryder, what are we going to use to derive it? The Pythagorean theorem. So I know that, and you know that, and you can use a variable if you like, but question mark squared plus x squared will be equal to 2x squared. Okay, so question mark squared plus x squared is equal to 4x squared. And we're solving for what this unknown side is. So that gives me 3x squared. Now when we take the square root, we can disregard the negative value. Why can we disregard the negative value? Right, because we're trying to solve for the length of a side, and you can't have a negative length. So we'll have our unknown side will be equal to the square root of 3. Now the square root of x squared we normally say is the absolute value of x to take into account that x can be positive or negative when we take the square root of x squared. However, because, again, we are talking about a side length, I can just say this is equal to root 3x. Do we follow that? So my unknown side is equal to root 3x. And depending on what x is equal to, that will give us the different side lengths, but that's the idea behind similar triangles, right? The angles will stay the same regardless of what those side lengths will be. You could imagine the triangle being stretched and kind of compressed.
So if you have the hypotenuse, you know what the hypotenuse is, you can just divide it by root 3 and then you know all the sides.
Say that one more time.
If you know what the hypotenuse is, you can divide it by root 3, and then you can like figure out what all the sides are.
First divided by 2 if you have hypotenuse.
Or yeah, like yeah.
You could use.
What she means if you only have one side.
Yeah, if you know what the hypotenuse is, and you
Or
can
any
figure
side.
it out. Yeah, if you know any side, you can figure out the other. And if
Because
you know
Pythagoras
it's
needs
30,
two.
60, 90 degree
Mhm.
triangle, then it will work.
Or you could use trig. Okay.
Go side by.
So we just derived the sides of our 30, 60, 90 triangle. And we're going to come back to that.
Now for the scary one.
No, 45, 45, 90, that's even easier. So if we know that two of the angles are 45 degrees, what do we know about the legs of the triangle? They're going to be equal. Okay, so here's my right angle. 45 degrees, 45 degrees. I'm just going to call this side X and this side X. I'm going to call this H. It's the unknown. We don't know what H is, but we want to get H in terms of X. So again, we can use our handy-dandy Pythagorean theorem, where we know x squared plus x squared is going to be equal to h squared.
Obviously.
So the left-hand side will become 2x squared. And then when we take the square root of each side to solve for h, again, we're dealing with the side length, so we can disregard the negative value, but we'll get root 2x.
Yeah, it looks a lot nicer.
Or you just
What looks nicer?
If you do x root 2.
Don't change it. Stick with your ways. Stay in
No, that
ground.
would make sense to me.
Yeah.
Stay in your ground.
Well, you guys can write it. You guys can write it however you would like in your notes.
Cool. That's respectable. Ooh, what's wrong with my brain?
Okay, so this is our other special right triangle. So we're going to just kind of hold off on those for a second. The only thing we're going to use right now are the angles from our special right triangle. So scroll down. Oh, sorry. Oh, sorry. So you guys, the next thing that we're going to do is derive the angles of the unit circle as well as some points that lie on the unit circle. You guys are probably wondering, what the heck is a unit circle?
Pizza.
Pizza.
Remember,
It looks like pizza.
second grade when you learned fractions, it was all about pizza.
Good, I remember that. Zah, dude.
Which that comes in handy
Zah.
now as well. Well, especially next class when we talk about
Do you
radians.
want some Zah?
Are you good?
Yeah.
Okay.
Let's go get some Zah.
Shh. So you guys, I want you to imagine that this is in the XY plane. Maybe draw, so the horizontal axis here, I'm just going to draw it. That's our x-axis, and then the vertical axis is our y-axis. So we are in the XY plane. Now, the equation of the unit circle is x squared plus y squared is equal to 1. And that's because this is a circle whose center is at the origin, and the circle has a radius of 1. Okay, that's why it's called the unit circle. Circle, it's centered at the origin and has a radius of 1. So just looking at this unit circle, without knowing anything else, this point right here would be the point 1, 0, knowing that the radius around the entire circle right, is 1. So the distance of any point on the circle from the origin is going to be 1 unit. This point up here would be 0, 1. What would this point over here be? I'm gonna switch. It's gonna get pretty colorful on here. So negative 1, 0. Hmm?
Oh yeah, that was Natasha. Because she thinks of colors as noises.
And what is this point at the bottom? 0, negative 1. Good.
Wait, you hear color, Natasha?
No.
Shh. So you guys, remember the quadrants, how we number the quadrants in the XY plane, right? This would be quadrant 1, quadrant 2, quadrant 3, quadrant 4. So we're going to start in quadrant 1. I'm going to get rid of my axis there, actually. So here, I'm going to use a dark blue. This angle right here is 0 degrees. We're starting at 0 degrees. We're only filling in the degrees right now. And the way that we're determining each angle is we're starting at 0, and then we're thinking about the ray being rotated. Okay, so this next angle is going to be 30 degrees.
How do you know that? Is it just a given?
Oh, because it'll go 30, 45,
Mm-hmm.
60.
In the unit circle, I'm just saying, at 30 degrees on the unit circle,
Okay.
right? So it's a picture, right? It might
So
not be, if we
The
get
hard
out.
one to find is the next one?
Next one's 45, the one after
No,
that is
I mean
60.
the line, because there are 2 lines in each unit circle. In each triangle-ish thing with the unit circle.
What?
There's the 30 with the degree, and then you go.
Ignore this
Yeah.
line until next time. That's going to be for radian measure. So for now, today we're staying in degrees for angle measure. Next time we'll discuss radians, because you guys haven't worked with radians before. Okay, so this first angle is 30 degrees. The next angle will be 45. And that next angle will be 60. That's from here to here. This angle is 30. From starting at 0, starting on the x-axis, and then rotating, this is 45. This is 60, and then this is 90. So that's quadrant 1, all the angles in quadrant 1. So we're going to use symmetry to help us figure out the angles in quadrant 2. So notice that going from 60 to 90 degrees is how many degrees?
30.
30. So what do we think this next angle here will be?
120.
120. We just have to add 30 degrees.
Are we going to do 360 degree or just 180 and flip to negatives? Like, is it going to be
You go all the
300?
way to
Do you go all the way around?
We
or
go
do you
all the way to 360 because if you rotate,
It's not like scratch.
it depends on the way you're thinking about the angle being rotated, whether or not it's positive or negative. But we're going to go all the way to 360. Okay. Now notice over here, going from 45 to 60 is how many degrees? 15. So going from 20, if we add 15, that'll put us at 135. And that's saying that if we were to start here and then rotate, this would be 135 degrees. Okay, adding another 15, right? We're adding 30 to 120 would put us at 150. And then if we add, right, this is 30. So if we add another 30, that puts us at 180. And any of you guys that do dance or sports or, I don't know, I think there's a lot of different places that you would talk about, like a 180-degree turn, right? That would be a half turn. And you can see we've rotated half the circle.
Why does it say 9:21 a.m. on the?
I don't know.
I like
That is
hallucinating
very
that,
wrong.
or-
No, it would usually military.
That's really strange, huh? Because that's the iPad too. I don't know. Okay, so let's fill in quadrant 3 and quadrant 4.
No idea that we did military.
What will this angle be in degrees?
210.
What is it? 210. Why is it 210?
Plus 30.
Yeah, we're adding 30 degrees, so that'll put us at 210. And then if we add 15 more, right, you can see where the smaller pieces of pizza are 15 degrees. So if we add 15, that'll put us at 225.
225. And then 240.
240.
And then 270.
270. Okay, shh. So now we're going to do quadrant 4. So if I add 30 degrees to 270, that'll put me at,
300.
add 15 more,
315 for the small pizza.
and then add another 15, and add 30, and we get to 360, which many of you already know is a full rotation.
Why do they put them at 30, 45, and 60?
On the unit circle, because you guys, so in geometry, you guys studied right triangle trig, right? Where you would find what sine evaluated or cosine or tangent evaluated at angles, what their outputs values were, which was, those outputs were ratios of the sides of right triangles. It's at these angles, we're going to start with quadrant 1. It's at these angles that you're able to evaluate the trig functions exactly. To find an exact value for the ratio that they're equal to, not some decimal approximation. There's some angles, like sine of 62 degrees, that you cannot find its exact value without technology, without like a calculator or I don't even think you could use a trig identity actually to find what sine evaluated at 62 degrees is. So some you do need technology. Okay, so now I'm going to go back to our special right triangles. And we're going to derive in the first quadrant what these points are. So to do that, I'm going to drop, what color should I use? Use pink. I'm going to drop a perpendicular here from this first point to create a right triangle. Okay, so this is a right triangle where this angle right here, please don't talk while I'm talking, is 30 degrees. This angle would then be 60 degrees, and then we have our right angle. On the board, just for reference purposes, okay, we derived that if this is 30 degrees, this is 60 degrees. This side would be 2x, this would be x, and this would be root 3x, right? Yeah. Here. Now, because we are in the unit circle, what does the length of this hypotenuse have to be?
1.
1.
Oh.
here that would make the hypotenuse equal to 1.
No, half.
1/2. So I'm going to replace x with 1/2. So this side would be equal to 1, this side would be equal to √3/2, and this side would be 1/2. So in our unit circle, the hypotenuse is 1, this side is 1/2, this side is √3/2. So we want to know what the x and the y value are at this first point. Looking at our right triangle, what would the x value be? √3/2. What would the y value at that point be?
1/2.
1/2, so the height of the triangle. Okay, does everybody see that? So based on the right triangle, this is a point that lies on the circle with a radius of 1.
Oh, I get it.
So I'm going to skip 45 for a second just so that we can still be in the 30, 60, 90 triangle. I'm going to switch this back to x. This was x. Okay. So this next point at 60 degrees, we're going to figure out what the x and y is there. So to do that, I'm again going to drop it perpendicular
Under there.
and draw a right triangle. So this, let's stay in green. Here's my right angle. This would be 60 degrees, and this would be 30 degrees. I apologize, I know it's kind of difficult to read. Right,
You drop a perpendicular going horizontal
No.
and vertical?
Nope.
Why not?
because 60 degrees is this angle here. We always start at 0 and then rotate counterclockwise for positive angles.
But isn't 60 30 away from 90? So you can make that one your 30? Like you start at 90 and then go clockwise, turn clockwise, and that's 30 degrees. So you can do a 30.
Oh, I see what you're saying. If you were to make
Yeah,
here.
I'm just talking about for the new one, the green one.
No, let's just drop the perpendicular from there. Okay. Now, what does the hypotenuse, what does this distance or this length for the side of the triangle have to be? 1. So, that's referring to the side opposite of, oh no, to the hypotenuse. So, what did I do? Oh, we could have left it, huh? We could have left it. That's, okay. We still have, this is 1, this is √3/2, and this is 1/2.
It's just the opposite.
We're with the same, yeah, it's just rotated. We're with the same triangle. I don't know why I took
Which
that
is
off.
1/2.
Okay, so this will be 1. The side opposite 30 degrees is what? 1/2. And then the side opposite 60 degrees will be √3/2. So x, Carter, what will x be at this point? 1/2. Kelly, what will y be at that point? by looking at the triangle, looking at the sides of the triangle, right? So this is going to, this side, right, is going to correspond to the x value of the triangle, or the x value of the point. And then this side of the triangle will correspond to the y value at the point. And then the last point in quadrant 1 would be this guy right here. So now we're going to drop a perpendicular to construct a 45, 45, 90 triangle.
Are we doing it on the notes or this?
You can do whatever you're comfortable with. Okay, so this angle here is 45 degrees. This angle is 45 degrees. Let me draw that guy up here. So from the sides that we derived, we said this was x, this was x, if this is a 45, 45, 90 triangle, and this was, the hypotenuse was root 2x. So we know that the hypotenuse of this triangle has to be equal to what? We're inside the unit circle. It has to be 1. So what do I need to make x equal to make the hypotenuse 1?
0. Just kidding, that doesn't make any sense.
1 over root 2.
1 over root 2, which is root 2 over 2. 1 over root 2.
Have a little room for it.
Now, the hypotenuse will be equal to 1. We do not like to leave a radical in the denominator, an irrational number in the denominator. So how do I rationalize 1 over root 2?
Root 2 over 2.
Right, but how do you get there?
You multiply it by root 2 over root 2.
Right, so you can multiply by a version of 1 to get root 2 over 2. This side will also be equal to root 2 over 2. Okay, so this side is 1. We have root 2 over 2 and root 2 over 2. I'm sorry, I know it's a little confusing with all the colors. So what is the, Abby, what would the x value of this point be?
Root 2.
Yeah. And then the y value would also be root 2 over 2, right? Okay, so we have all of the points on the unit circle right now in quadrant 1. And we're going to use symmetry to allow us to fill in the points in quadrant 2 next, and then we'll do quadrant 3, quadrant 4. Okay, so looking at quadrant 2, at 120 degrees, the point that's on the circle at 120 degrees, isn't this point just a reflection of this point over here at 60 degrees about the y-axis? So what would this point be?
The comma, the root of 3 over 2.
Perfect. Negative 1/2, comma, root 3 over 2. And we know in quadrant 2, the x values are going to be negative and the y values will be positive. Okay, the point at 135 degrees is a reflection about the y-axis of the point that's at 45 degrees. So what would the ordered pair be at 135 degrees?
Negative 2 over root 2. Negative root 2 over 2.
Yeah, negative root 2 over 2, right? Okay.
That's what I meant.
So negative root 2 over 2, comma, root 2 over 2. And then how about at 150 degrees?
Negative root 3 over 2.
Okay, and then we already have negative 1, 0. Okay, so let's use quadrant 2 to help us fill in quadrant 3. Stick in pink. Okay, so at the point that's at 210 degrees, we could think of as a reflection about the x-axis to the point that's at 150 degrees. So what will the ordered point be at 210 degrees? Okay. And we know both the x and the y's should be negative in quadrant 3. Okay, at 225, the point will be.
Negative root 2 over 2, negative root 2 over 2.
Hey, Carter, do you want to flip on the fan? Thank you. Okay, and then Natasha, what do you think the point will be at 240?
Negative 1 half and negative 3 or negative root 3 of 2.
Perfect. Okay, we're on to the last quadrant. So we could use quadrant 1 or you could use quadrant 3 to help you figure out what the points would be. What will the point be at 300 degrees?
1 half negative root 3 over 2.
Good job, Helen.
You taught hard.
Good job, Carter. You know why?
Writer. Miles, what will the point be at 315?
At 315, the point will be negative root 2 over 2, and then 1 over root 2.
Well, we're in quadrant 4, so what should the sign of x be in quadrant 4?
Oh, yeah, it should be positive. Oops,
So it'll be root
that's just
2 over
because
2,
of the little line, it was
negative
a little
root 2 over 2. I know, it's kind of crowded on here.
This root 2 over 2.
And then our very last point at 330 degrees, since we already have 360 filled in. Case, do you want to give me the point for 330 degrees?
root 3 over 2.
Perfect. Okay.
Radiant is probably very scary.
Radians will be next class. So let's hold off. We're going to kind of put the unit circle aside for a second. Let me name this. This is the famous unit circle. Okay, now we discussed this a little bit at the beginning of class, but SOHCAHTOA. So SOHCAHTOA, let's talk about what that means. SOHCAHTOA is the little phrase, what would you call that? Acronym to help you remember right triangle trig. So it refers to the three main trig functions, sine, cosine, and tangent, where the input values are angles and the output values are ratios of the sides of right triangles. So sine of the angle theta, have you guys seen theta before used for angles?
Yeah.
It's like a little thing with like.
Yeah, it's a Greek letter, and we're going to use it a lot to represent an angle. So sine of theta is equal to, OH, so that's opposite. So the side opposite the angle theta over the hypotenuse of the triangle. of the right triangle. Cosine theta, this only applies to right triangles. Cosine theta, AH, refers to the side adjacent theta over the hypotenuse. And then TOA, that's tan of theta, is equal to the side opposite theta over the side adjacent to theta. So I'm going to copy and paste my, my triangles that I had before. Am I going to get the purple?
Yeah.
I don't want the purple.
You can just erase
I don't
it.
even want the question mark. There we go. Copy. You can't do what?
She said we can't do that on paper.
I'll make this, you guys, I'll make this video available to everybody if you want to reference it.
Ooh, I feel like we should start doing this for every single time we do ours.
What?
So we can listen to it.
Yeah, but would you guys really pay attention in class then?
Yes.
Yeah, who would want to listen to this stuff at home? No offense.
Wow.
But like, why would you want to listen to it again?
We said two.
Why, it's like-
I'll take it into account. If people are absent, I'll definitely think about it because I can see its usefulness. Okay, you guys, so knowing what sine, cosine, and tangent are equal to. So if I wanted to find what cosine, and please don't shout out answers right away. So if I wanted to find out what cosine of 30 degrees is equal to. So cosine is adjacent over hypotenuse. So I look at the side adjacent to 30 degrees, and that side length is root 3x. And then the hypotenuse is 2x. So it would be root 3x over 2x, where the x's would cancel. And we would just get root 3 over 2.
Which is like the coordinate.
Sine of 30 degrees. So sine is opposite over hypotenuse. What's the length of the side opposite from 30 degrees? X over hypotenuse, which is 2x. So that's just 1/2. I feel like I just made the pen skinnier without meaning
You're
to.
not pressing down hard.
No, it's speed, right?
Interesting.
You can change it back to thickness.
How do I do that? Just on this?
Yeah. It's on the left, that part. It's just pressure sensitivity.
Yeah,
Apple pencils. You want things?
Okay.
You draw on your iPad and then just sync it into your iPad.
Tangent of 30 degrees. Oh, see, now it's thicker. Shh. So tangent of 30 degrees. What is the side opposite 30 degrees where you said it's x? And then the side adjacent to 30 degrees is root 3x. So that would be 1 over root 3, where if we rationalize, we get root 3 over 3. Now, let's go back up to quadrant 1 in our unit circle. So, you guys, what was cosine of 30 degrees?
3 over 2.
Root 3 over 2. And what was sine of 30 degrees? 1/2. Okay. Let's go to 60. Let's look at 60 degrees. Let me add a page here.
Probably, yeah, exactly.
So if we wanted to find cosine of 60 degrees, looking at our right triangle, okay, adjacent, well, the side adjacent to 60 degrees is what? And the hypotenuse is 2x, right? So we get cosine of 60 degrees is equal to 1/2. Sine of 60 degrees. Sine is opposite over hypotenuse, so opposite would be root 3x over 2x, so we get root 3 over 2. So going back up to our unit circle and comparing, so at 60 degrees, you guys said that cosine of 60 degrees was equal to 1/2. Sine of 60 degrees was equal to, okay, so are we seeing how our unit circle is connected to sine and cosine? In the unit circle, cosine of theta corresponds to what?
X value.
The x value. And in the unit circle, sine of theta corresponds to the y value. Or we could write that as x comma y will correspond to cosine theta comma sine theta. So if I wanted to know, you guys look at your unit circle and tell me what is cosine of 225 degrees? What is it? Negative root 2 over 2. So I go to 225 and I look at the x value and yep, negative root 2 over 2. What if we wanted to know sine of 120 degrees? What's sine of 120 degrees?
Root 3 over 2.
Mm-hmm.
How do you derive sine and cosine again? Is it just magic?
Well, we talked about them as being ratios of the sides of right triangles, right? So their inputs are angles, and then their outputs are ratios of those sides. But now, knowing the unit circle, so before you guys were only able to really evaluate sine, cosine, and tangent for acute angles, right? Angles that could be angles in triangles, right triangles. But now with the unit circle, you can evaluate sine, cosine, or I'll show you how to evaluate tangent in a second, with any angle that lies on the unit circle. We're almost done, you guys. See you peeking at the clock.
The time stays the same.
Yeah.
That's so weird. I wonder if it's because I'm recording, maybe? But it wasn't 9:41 when we started. I don't know.
It probably is. It probably just like a
Just chooses a random time.
There's probably some importance in that.
Decoders.
So you guys-
We're basically done. Just have it be random.
I'll be smart idea. Play a game and try and get it to a certain time.
You guys, let's look at this ratio. So if I took sine of 30 degrees and put it over cosine of 30 degrees, well, what is sine of 30 degrees? Look at your unit circle and tell me what sine of 30 degrees is. Or we already determined what it was, right? 1/2. And then what was cosine of 30 degrees?
Root 3 over 2.
Okay. So that's saying 1/2 times 2 over root 3, which is 1 over root 3.
That's the tangent.
That's the tangent. That's also equivalent to tangent of 30 degrees, right? We had already found that using right triangle trig up here. So the other new thing from today,
Wait, can we
go back up,
no, just stay there.
stay here. So tangent of theta is the ratio of sine over cosine, which since x is cosine on the unit circle and y is sine on the unit circle, if you take the ratio y over x on the unit circle, you can find tangent for any angle on the unit circle. Depending on the information given, sometimes tangent's more useful than sine or cosine.
Like, what do you think? Like, why is it more useful?
So if you're solving for some unknown value that's maybe not measurable using like a ruler or anything like that, like if I wanted to know how high that tree is, okay, and I'm standing on the football field and I can measure how far away I am from the tree.
Those are the
Or I guess I could measure like from me to the top of the tree, and you could measure how tall the tree is.
It was a bonus in
Oh, it's
8th
the
grade.
firefighters
It was a bonus
too.
in 8th grade, and I got
They're
the
the ones
question
with, like,
right
the-
because I had no idea what was going on, and I guessed, and I got it right, but then they didn't give me any credit. I was very angry.
It's because it's like the
I'll never
firefighter
forget
one because
that.
it's like the building and then there's the window that they
I
gotta
did
get
know
through,
that.
but they're standing like on something.
I know this well.
So he's a big mate.
I love it when they're like.
Okay, now sine, cosine, and tangent have been defined as different sides of the right triangle. We just defined sine and cosine as x and y in the unit circle. Now, in the unit circle, any point that lies on the circle is going to be how far away from the origin? 1 unit. So, for defining the trig functions in the Cartesian plane, so any point that lies in the Cartesian plane, r represents the distance of that point from the origin. So the 3 trig functions, these are the 3, oops, that's not what I meant to do. These are our 3 trig functions in terms of x, y, and r. So x and y the ordered pairs that you could define a point in the Cartesian plane, in the xy plane. And then r represents the distance of that point to the origin. In the unit circle, r is always equal to 1, so it makes sense. You can see, looking at sine of theta is equal to y over r. Well, if r is equal to 1, then sine of theta will be equal to y.
Oh.
Cosine of theta is equal to x over r, but if r is equal to 1, cosine of theta will just be equal to x.
What is CSC and
These are the reciprocal trig functions that we'll talk about next time. So there's 6 total trig functions, and we will talk about the reciprocal trig functions next time.
The last one's
CSEC?
cotangent. The last one's cotangent.
Shall we talk about
CSEC?
your
Sec
homework?
and cotangent.
Shall we talk about your homework?
Yeah.
About our homework?
Your homework.
How about our not homework? Sorry.
Your only homework is to learn the unit circle, like memorize it.
Wait, like all the
You need to know all of the degrees and all of the points. You now know how to derive it. So basically, if you know that first quadrant, you can figure everything else out,
Yeah.
right? I'm giving you a maximum of 10 minutes on the homework quiz next time. You need to become fast with this, especially next year. Mr. A is expecting you to, the way he puts it, is if your dog or cat jumps on top of you in the middle of the night and asks you, what the cosine of 315 degrees is, you should be able to answer it like that. Okay?
That's because you're looking. Thanks, Kelly.
You should be able to draw the unit circle, but you should also be able to visualize the unit circle in your head to figure out or to evaluate a trig function at one of those angles that's on the unit circle very, very quickly. So the first step to being able to do that is to memorize the unit circle. So for this first one, it'll just be with the angle measures in degrees and all the points around the unit circle. After next class, you'll also know radians, so it'll be the entire thing. Next Friday, I have our official unit circle quiz contest where the person that has the fastest time in accurately filling in the unit circle will get
It's memorization.
a prize.
Is it like,
Can you tell
is
me?
it like apple pencil
No.
prize or like pencil prize?
In between. It's in between.
Alright.
It's a nerdy prize.
I swear if it's candy.
But it's not candy. It's a nerdy prize, but it's only fitting that it would be a nerdy
it's not
prize.
like a dictionary or book or
It's not a
anything.
dictionary. Alexis had her hand up and I cannot hear her question.
Are we gonna like do quiz next class or is it just a
Yeah, it'll be a quiz, but you'll get maximum. I'm going to cut it off at 10 minutes. I don't think anyone will need 10 minutes. Now, I think I have already emailed you blank copies of the unit circle.
Is it basically you'll give us this and then
Yes.
fill it out?
Yes.
Wait, and this is. I'm gonna time myself.
You're gonna take the whole thing and still just be like, why
It's not that hard.
raise
This
or
is like
something,
common sense.
right?
Yeah, you can add.
It'll be, so what I would do is take the percentage that you got correct, and so it'll be a quiz out of 10. So I'll take the percentage you had correct. And use that.
Yeah, but like no, I mean like the unit circle is the radius always the radius.
Yeah, that's why it's a unit.
Oh, yes, I'm sorry, I didn't catch. Yeah. So any point is going to be a distance of 1 unit from the center.
I'm like, we're out of this. Oh, no, don't send that out.
Do you guys did get the email that I sent
Yeah, I
out
did.
late one, right? Along with the keys?
What are we doing?
Oh, the last, hey, don't put your stuff away yet. The last thing that I want to show you is I just told you guys about evaluating sine, cosine, and tangent using the unit circle. For memorizing the sine, you might notice on that blank one that in each quadrant it says positive, negative. That refers to the sine of the ratio that you would get for sine, cosine, tangent, or any of their reciprocal trig functions. And the way that you can memorize it, I know it kind of seems silly knowing that, but you'll see when we're actually using the trig functions for different applications and such, that it's definitely useful to know what the sign of each trig function is in each quadrant. Now the way that you can remember this is all students take calculus. In quadrant 1, all students take calculus.
What's like the letters for DNA only without a G?
All of the trig functions are positive in quadrant 1. Since x and y are positive, right, and it's different ratios of x, y, and r. So r is always positive, x and y are both positive in quadrant 1, meaning all of the trig functions will be positive. In quadrant 2, sine and its reciprocal, cosecant, are positive, and all the others are negative.
Do we need to know this for next class?
No. In quadrant 3, tangent and cotangent and its reciprocal are positive. And in quadrant 4, cosine and secant are positive, and all the rest are negative. All students take calculus. So you read it the same way you read you number the quadrants, right? 1, 2, 3, 4.
That would make sense.
I know this is a lot. I know deriving the unit circle it's a lot. So that's your only homework is to practice and memorize that. You
But
have your blank
9.1.
unit circle, and you can put it into Notability, or you can print a bunch out, and you can just practice filling them in. That's it. And
That's a
Do you know
lot.
that in her commencement
Don't argue.
address,
Accept
it.
Over.
argues that citizens in the South and hope is constructive?